Assalamualaikum dear students. Today our lecture is about groundwater hydraulics. We will also study Darcy Law and a brief introduction about the groundwater movement and the method how we can measure the direction of the flow and then well hydraulics, its their derivation and a brief introduction about the governing equations for the groundwater movement. First of all, let's have a uh, kind of revision of the previous uh, basic introduction to hydrogeology. What is an acute? So it is a unit of rock or layer of rock which is impermeable to fluid and it acts as a barrier to fluid flow. And one more thing that this acute is not permitting any kind of water movement inside or outside this uh, geological formation. Then we have two other aquifers, very commonly known as confined aquifer, which is lying in between two aquifers. Not necessarily aquifers, but it can be aquiclude as well. It can be aquifuge as well. So any kind of condition can be existing in this case. We have studied three conditions in the previous lecture. You can go through those once again. Then we have unconfined aquifer, which is not bounded on the surface side, and the water is free to move and at the surface of water having atmosphere. So this is the distribution of groundwater is different zones. So we have soil moisture zone, usually top layer. Then we have zone of aeration, meadow zone, capillary fringe, which is a transition between the saturated and unsaturated zone. On the top of the aquifer, it has a negative pressure, and water is being traveling against the gravity in this zone. Then we have zone of saturation, phatic zone, in case of unconfined aquifer, which is fully saturated, contains ample quantities of water. Um, Water enters the groundwater systems at recharge area and then it leaves the system at discharge areas. Here is one of the very comprehensive figures explaining confined aquifers. We have an area of recharge on the left side, and the water is being infiltrated into the aquifers. And this red line is showing the potentiometric surface. That means that the water has the capacity to rise up to this. So, because in confined aquifers, the water is under hydrostatic, so that's why it has the capacity to travel to higher levels within a well, within a spring. So, in most of the cases, in of artesian conditions, you have observed that the spring which is flowing from this confined aquifer is normally existing for a specific duration because the quantity of water is not sufficient enough to continue it as a source. So in most of the cases, the springs get dry with the passage of time. And this is another description, and you can find unconfined aquifer as well in this case. So this is again this is the recharge area, and then this is the potentiometric surface for the confined aquifers. This is the level up to which the water has the capacity to rise, and this is the unconfined aquifer, which is having a water table level with the atmospheric pressure. So this pressure is equal to the surface pressure. That's why we are declaring it equal to atmospheric pressure, and the water is free to move in this aquifer. And this is flow direction based on the slope of the head. Is again a description in which you can distinguish the recharge area and the discharge areas, and we can also predict the water movement. The water is flowing towards the discharge area, and because it is a confined aquifer, you can see that in this case we are having the different layers of water storage for different time durations, because the water movement is very much restricted in this case of aquifer. Again, this is another description of aquifers, and here you can see unconfined aquifer, confining bed, which is separating it from the confined aquifers. So, in case of unconfined aquifer, we have a free movement of water inside this aquifer. Then, the confining bed is making the boundary of this unconfined aquifer, and below this confining bed we have a confined aquifer in which the water is going to be retained for longer duration. So if you see here, there is an artesian pressure if we are going all the way down into the confined aquifers, which is giving us the potentiometric surface here. But in this case, we are having the atmospheric level with this much level, water water level rise in the uh, well, in the case of unconfined aquifer. So this is the case for unconfined aquifer, and this is the case for the confined aquifers. And again, it is a much more detailed description for the unconfined aquifers, because we are having water table level here, and we have also the capillary fringe here. So kind of distribution you can see. This is the unsaturated zone, a dose zone as well, and this is the saturated zone. So if we call it a Vadose zone, then this part will also be included in it. But now we are separating it based on the saturation level. So that's why this 100% saturation is also shown in this saturated zone. Well, another description, I think you can have a view by yourself. Um, it's like the same. This is the perched water table level as we described earlier. This amount of water is not sufficient enough to be drawn, and it is separated from the other zone by the aquiclude. So aquiclude is having water, but it doesn't have the capacity to transfer. And in case of unconfined aquifers, we have this much flow of water. It is flowing directly into this stream like a discharge. So this is the discharge area, and this is the recharge areas. This is the confining bed, and igneous rock is separating it and giving it a platform to store the water in this aquifer. These are about the geological formation which are going to describe our groundwater systems and their different kinds and different scenarios. Now, something about the groundwater movement, as we earlier discussed as well, that the movement of groundwater is directly related to the pressure head, hydraulic head, which is going to provide a slope, and based on that slope, the water is going to flow normally, and the path through which the water will be flowing, it is through the pores, voids within the geological structure. So in this case, water table is actually a sloping surface. Slope is the determined by the difference in the water table elevation. This is the hydraulic head, and over a specified distance L. So this L is the length up to which we are taking the considering the movement of water, and at the same time we will be having a hydraulic head difference. So this and this, these are the 2 points which are giving us this hydraulic head. This is the difference in the elevation of water level, and this will be divided by this to get the hydraulic head. This is how we can determine the slope through which the water will be moving. And this is something about the cone of depression, which is obtained while the water is being drawn and water is being discharged. When water is discharged through a pump, especially heavy pumping, we are normally getting this kind of cone of depression. So the water table level in this area is going to reduce to this much level because of the excessive drawing of the water, with withdrawing of the water from this well. So higher the pumping rate, the deeper this cone of depression will become. And and one more thing that we are going to obtain it in the form of contours. This is only one direction in which two directions in which we are watching it, and if we are observing it from the top, we will be observing it in the form of circles, and those circles will be actually the uh, contours of water table elevation, water table head. So it is very important to define water table level in terms of the potentiometric surfaces, um, potential equipotential lines. So those equipotential lines will be actually describing the water table level. This is something how we can trace the movement of contaminant in our groundwaters. Especially if you are working on a contaminated, you are supposed to find out the path on which the contaminant is to travel. So if this is the main source of contamination in an uh, subsurface strata, then we are also interested to know in which direction the water will be moving. This contamination will be moving. So in that case, we will be also finding out different other water wells, and their characteristics regarding the quality of water. We can have a monitoring well here, we can have a monitoring well here, then we can observe their characteristics, their qualities, and then we will find out that in this well the water is getting contaminated, while in this well the water is not getting contaminated. So because of this difference, we can distinguish that in which direction the water, the contamination is likely to travel. Here is again uh, the impact of monitoring wells, and how the uh, cone of depression changes the direction of contamination. This is a previous case in which we simply studied the movement of contaminant in a typical direction following the uh, slope, normal slope. But in this case, you can observe that we are having a um, heavily pumped well here in this the opposite direction. So normally this is the usual flow direction of water based on the hydraulic head. But at the same time, you can observe that this heavily pumping well is installed here, which is shifting the cone of depression in this direction. When water table level is reducing in this area due to the cone of depression. Then all the contamination existing in this at this point will be shifted to the reverse direction, and it will be under the influence of this cone of depression. And now, due to this shifting of water table level, this installed uh, monitoring well will be having all the contamination in it. So initially in this previous case we found the contamination to be following the flow of groundwater. But in this case, it is under the influence of the uh, cone of depression. So that cone of depression has shifted the groundwater level. Correct. So again, in this figure, you can clearly differentiate how the cone of depression affects of the water table levels. So in this normal case, normal flow, the wells are there are three wells which are having a normal cone of depressions based on their level and discharge rate. But here in this case, the cone of depression has uh, become deeper due to the higher rate of the water extraction from this well. And due to this higher water level extraction, the water table level has first of all reduced, and then it has become deeper as well at this point. So comparing both, you can observe that here we are having a much deeper level of water, but the water quantity is the same. So here we are having an effect of this cone, and now this water table level is not included in the uh, range of this well, and now this well has become dry well because it is not accessing this water table level due to the deeper cone of depression and due to the higher rates of the water drawing. And again, it's now in this figure you can easily observe the role of our geological formations. What kind of role these geological formations play in the movement of contaminant from one place to the other. So in this case, we are observing that we have a hard rock here lying beneath this water flowing, and there is no much penetration of the contamination within the subsurface. The water is likely to flow on the surface of the water table and moving along the direction it is traveling all the way to this well. In the second figure, you can observe that we are having this kind of geological formation which is permeable. So it is allowing the water to penetrate down into the soil. It is reflecting much more percolation down into the soil and then into the groundwaters as well. So if you see here, it is the septic tank and it is moving downwards as well as the water is traveling in this direction. It is allowing the contaminant to dilute, and so first of all it is diluting on the way downwards, and then while on its way it is not in that quantity which can be called contaminated. So due to this percolation, due to the deeper soils, and furthermore due to the dilution, the role of this contamination has very much reduced. So it is very much dependent upon the geological features, geological formations, and geological structures which are existing beneath the contamination source, that how it is going to behave for the movement of contaminant along with the water or the pores. Now, something about the movement of groundwater movement. We talked earlier, it is all based on the hydraulic head, and it is the driving force that moves water. The hydraulic head combines fluid pressure and gradient, and then under that uh, the water is supposed to move in a typical direction. So, an important parameter which is necessary in defining the movement of describing the movement of groundwater is the hydraulic conductivity. It is expressed as K, and it is the rate at which water moves through material. This material is the medium through which it is going to move, and the internal friction and various parts of water takes are factors affecting hydraulic conductivity, and hydraulic conductivity is generally expressed in meters per day. So it is the cross section through which the water is moving in unit time. So that is a vector quantity. It is quite similar to the phenomena of permeability, but in permeability it is a scalar quantity. We are only talking about the movement of uh, groundwater under the effect of the pores and voids. But in this hydraulic conductivity, we are actually defining quantity of water moving in a particular direction through a typical and specified cross section. So that's why it is and furthermore in a particular time as well. So first of all we are defining the area, and then we are also defining the time, and so this is the factor which will be important in describing the quantity of water as well. In the coming slides we will uh, discuss it in detail. This I think we have already talked. Uh, Movement depends upon the sediment properties and the porosity, permeability, specific yield, specific retention. I hope you are very much clear with the specific yield and specific retention by now. So grain shape and cementation also affect the porosity, because porosity is not only affected by the voids, pores, but it also affected by the interlocked fragments of that solid particle, that soil particle. So in case that the soil particles are interlocked, then it also can have effect on the movement of groundwater. Uh, Thus, porosity will be different. We normally declare the that porosity as effective porosity, because that effective porosity is what actually providing us the specific yield. We will talk about it in the next lectures, next slides. Water table level, I think we are already clear. The water table contour lines are also called equipotential lines. That's what we talked in the previous slides when we talked about the cone of depression. And those contours are actually describing the equipotential lines. So this is the slope. We talked about it already. I think you can go through the slide as well. This is something how we can determine the groundwater movement. It is very interesting and very useful method to determine the groundwater flow in a typical direction. For this, we must have a data about the three different wells of about which we are sure about the water table levels, we are sure about their surface elevation. Talking about these 3 points, so well number one has an elevation of this, and it has a depth of water table up to 120. So subtracting this from this will give us the water table elevation. This is the water table elevation for this well. Similarly, this is the surface level of well 2, and this is the depth to the water table 78, and giving us the water table elevation that is explained here, this one. Similarly, for the well 3, we have this much the elevation, surface elevation, and subtracting the water table depth is 95, we will get the water table elevation. So all these water table elevations are actually the points at which we are having water table level. Now we will be dealing with this water table level. So let's have this whole line divided in equal cross sections, equal points, and then let this line be also divided in equal sections, equal segments, and then this line may also be divided in equal segments. So these segments are representing us the different levels of elevation. So these are different levels of elevation. So let's make the contours. So we can easily make the contours based on the same levels of elevation. So for example, this is one of the same level of elevation, 4280 elevation, and this is 4280 elevation on this line, 4260 elevation on this, and 4260 on this line, and then 4240 and 4240. This is the point. This is the point here, and for this line, this is the point. Same, this is the point here, and this is the same point here. We will be joining these points. So we are having these straight lines which are joining the same elevation levels. Now next step is we are going to make a perpendicular line from every straight line. So just make a straight perpendicular line in this direction. For this line, we make a perpendicular line. For this line, make a perpendicular line. Sorry. For this line, again make a perpendicular line. For this line, again make a perpendicular line. For this line, make a perpendicular line. For this line, make a perpendicular line. Then, using the head to tail rule, we will be joining all these straight perpendiculars by head to tail rule and using graphical method. So we will be having uh, resultant of all these vectors, and we will be joining all these vectors by head to tail rule and getting the resultant vector. That resultant vector is shown here, and this resultant vector is actually giving us the direction of water movement. So this is a very interesting and useful method to determine water movement. So please go through it by changing the different values and then finding it by yourself and solving it on some graphical paper to actually observe how we can make this graphical representation on the graphs. This is again, I think, kind of a repetition working on the porosity, about the voids. This is the permeability, we talked about it as well, specific retention, specific yields, and all this we have already gone through. Hydraulic conductivity, we talked about it earlier. So how these our geological formations affect the groundwater movement? We have studied the concept of well sorted, poorly sorted, and then well graded, poorly graded. I think that's quite clear. And now, based on that, you can easily differentiate how these water movement can be affected by the this kind of situations. So, well sorted is having same kind of pores, same kind of solid particle, and it is giving us wider spaces. So that means it is allowing us to the water to flow easily through these pores. But when we talk about poorly sorted, like coarse and fine mixed, then the finer particles will uh, occupy the space between these coarse particles, and then it will obstacle to the movement of water through these voids. And in this case, we are having a silt clay combination which is not allowing the water to move through them because there are least voids present between these finer particles. Thus, in this kind of structure, we don't have any kind of voids available. And even if we have the voids on the top surface, the top layer will be normally covered with the water, creating a surface tension on the surface, which will further create an obstacle and hindrance to the flow of water from the top to the bottom. That's why it is the least permeable structure which is allowing the water to move. So the permeability and hydraulic conductivity is moving on this side where we are having open voids for the water. So these are the conditions which will be considered for groundwater movements, and based on the hydraulic, geological formations. So it's kind of two considerations we have already studied: steady and unsteady flow conditions, and confined and unconfined aquifers. And then uh, two basic equations which will be used will be like using Darcy Law and the conservation of mass. So these are our tools to determine and to make the groundwater flow equations. All the groundwater flow governing equations are based on these principles. All the models, all the softwares which are predicting the groundwater flow or which are predicting the groundwater contamination movement are all based on these scenarios and these uh, equations. So what is Darcy law? Basically, it is going to define, it is going to provide us information how much groundwater is flowing, how fast it is moving, what is the velocity of the groundwater, and where groundwater flows, in which direction it will be flowing, like this. So this is one of the cross-sectional volumes. Then this is the metric heads and giving us potentiometric surface in a typical. So normally the linear flow path assumed in Darcy law will be like this. But actually the flow will be is like this. It is the true path, which is tortuous path, which is not equal to the normal this length which is observed in the linear flow path. So specific discharge is equal to uh, Q over A. Q is the flow rate, and this is the specific discharge. We can also call it flux, and this is the area. So kind of this specific discharge is kind of velocity. The flux as well as it is kind of velocity. It is discharge as well. So every linear velocity will be expressed in this term, and you can see that V is equal to Q over A multiplied by N. A is multiplied by this N. So this is N is equal to effective porosity. So what is effective porosity? It is the only path through which the water is actually moving. It is not the straight line or cross-sectional area, but it is the effective area through which the water is moving truly. So flow, and I think we have done it. This is the Darcy law. So, and here is the equation of Darcy. Q is equal to KIA. So, Darcy's experiment is normally conducted in our labs, and which is actually having this kind of column, this kind of setup through which we have some typical medium, and the water is allowed to move through it. We are providing it some head as well. We have the length, and we will determine how much time it will take and under what conditions it will be moving. So this is the hydraulic conductivity, uh, hydraulic gradient I, and this is A is the area through which it will be moving, and then this is the actually is the flow rate through which it will. So this is something about the determination of different parameters. So Darcy investigated groundwater flow under the controlled conditions using the experiment as shown in the previous slide. So what is the discharge? Q. It is the flow rate, which is directly proportional to the hydraulic head, and this flow rate is directly inversely proportional to the uh, delta x, which is the distance, and then this is again directly proportional to the cross-sectional area. So flow rate, Q is the volumetric flow rate, A is the cross-sectional area, and then we are explain our Darcy law in the terms of these parameters. Q is equal to KIA. So that K will be the hydraulic conductivity. This is H1, this is H2, this is the delta H, this is the slope delta H by delta X. This is the hydraulic gradient equal to the slope. K is the proportionality constant, which is added to form the following equation. This one. I think now this equation is clear. Well, the velocity of groundwater is based on the hydraulic conductivity as well as the hydraulic head. So velocity is equal to K into I. Now, the equation to describe the relation between subsurface materials and movement of water through them is Q is equal to KIA according to the Darcy law. Q is the discharge volumetric flow rate, volume of water flowing through an aquifer per unit time. A is the area through which the groundwater is flowing, cross-sectional area. Now, simply rearranging the equation to Q over A equal to Ki. Q over A is equal to Ki, known as the flux V, which is an apparent velocity. Now, this is the apparent velocity which is actually taking place based on our experiment and on the real ground conditions. So actual velocity is equal to the Darcy flux and it is equal to the Vx. Now this flux is also called discharge and so this flux is also called specific discharge and represented by Q, length over time. Actual velocity, groundwater velocity, is the Darcy velocity, Vx, and it is equal to seepage velocity. And now it is greater than the flux is equal to Darcy velocity and apparent velocity, and also called the ideal velocity. It is because now the area has been reduced. How this area has been reduced? Because now we are not covering the whole area, cross-sectional area, but we are only including that area which is multiplied by porosity, A by N. And now what is this N? It is actually representing the porosity. Here Vx, which is the flux, is equal to Q over A into N. N is now the effective porosity, and multiplied by the area, and is equal to Ki over N. Now this N factor is actually included in this case, and because of this, our this velocity will be increasing. This N is supposed to be less than 1, because it is the proportion, it is the ratio. So that's why we are going to have this value always higher than the actual the apparent velocity found by the ideal velocity. So this was something about the Darcy law, and especially the difference between this Darcy flux and the Darcy velocity. Darcy velocity is a superficial velocity. Actual velocity V is the volumetric flow rate per unit area of connected pore space. Therefore, V is equal to Q small q over N E. And this is the representation. We have already found it in the previous slide, where NEA is the effective area of flow and NE is the effective porosity. V is the linear velocity of groundwater. V is always larger than the superficial velocity, and it increases with the decreasing effective porosity. So these are some of the explanations. I think these are just the equations. So I think please go through this slide as well. It has already been explained just for your information. So A is equal to total area, AV is the voids, and this A voids will be A multiplied by N. So this is something about the derivation. Now, when we summarized that what we are going to adopt, we mentioned Darcy law and the law of mass conservation and continuity equation. So we will be using continuity equation in this case. Q is the flow charge is equal to A into Vd is equal to AV into Vs. So where Q is the flow rate, A is the total cross-sectional area, AV is the area of voids, and Vs is the seepage velocity, Vd is the Darcy velocity. So this is the situation, actual situation. This is the ideal situation. Both are equal to the flow rate. Vs is equal to Vd over into A over AB. Then multiplying both sides by the length L, and then where Vt is equal to total volume, Vv is equal to void volumes. By definition, Vv over Vt is equal to porosity. And thus, we will be getting Vs is equal to Vt over N. So I think this is quite simple. You can derive it by yourself. So V or Q is the specific discharge, and Darcy velocity. I talked about it earlier, that this discharge is actually the velocity. So indicates the V occurs in the direction of the decreasing head. Specific discharge has units of velocity. So all these things will be used in this, and now the equations of groundwater flow, which will be actually uh, describing the flow movement and then contaminant movement, are based on the Darcy Law continuity equation, conservation of fluid mass, and Laplace equation. Based on these, we are going to have the equations like this, which will be in the coming lectures. So for today's lecture, that's all.